Okay, so today we are going to begin our excursion into the field of rational functions. The first step in doing this is to actually consider a function that is also a rational function, but is a very specific type of rational function, and that is called the reciprocal of a function. Now, before we begin, you may already know what the reciprocal is. In just plain numbers, if you have a number like 5, its reciprocal, I'll just call it r, is going to be 1 over 5. Okay? So with the same idea, we have for the function f of x, its reciprocal is just the function 1 over f of x. So for example, if I have the function x plus 3, its reciprocal is just the function 1 over x plus 3. Now what we are interested in, and our goals for today, so the goals for today are to figure out what properties of the reciprocal function r can we deduce from f, and how do we graph r. Okay? And for the purposes of what we are doing today, we are only going to be considering f. So this is a simplification of the problem. We are going to consider the case where f is a polynomial, and for the most part, usually we're going to consider f with degree 2 or less. Okay? However, a great many things that we are going to say today about these reciprocal functions will be true in general for just any f of x. I will point those out when we get to them. Okay? Alright, so the first big warning that I'm going to leave up on the board I'm going to try to leave it up on the board as long as I possibly can, because this is a huge warning, and you're guaranteed to make this mistake at least once if you're not careful. Okay? So here's the huge mistake. Okay? Normally with numbers, we write the following. If we want to write 1 over 5, this is the same thing as 5 to the negative 1. But for functions, if you're writing 1 over f of x, this is not the same thing as f to the negative 1 of x. Recall from section 1 that this notation means the inverse of f. Okay? And we are actually going to prove as an exercise that it is not true in general that 1 over f is the inverse function. Okay? It is not true in general. Okay? And we are actually going to do an example of this in just a second. Let's see. So, let's do this quickly. So our example here, I'll just put the example x and 1 over x. Okay, this is the example that we're going to consider right now. So I got a new color today, it's blue. We got rid of the purple finally. Let's try it out. So we have our function f of x, oh that's nice, is equal to x, and therefore the reciprocal function 1 over f of x is equal to what? 1 over x. You just put a 1 and then the function goes in the bottom. Okay? So this is after taking the reciprocal. I'll call this r. Well, like r is just a way to like represent you're taking your function and you're turning it into another function. Okay. I won't say too much more about that, or else I'm going to go off the deep end with some of the stuff that I'm doing. But okay. Let's see. And what is the inverse of f of x? Well, we can figure that out very easily. Remember, our procedure just involved us switching f of x for y, and then we just have to switch positions of x and y, and then solve for y, but you know what? That's the exact same thing, so we didn't even have to do anything. And I mean, that makes sense, because just graphically, if you think about it, if you take the line y equals x and reflect it across the line y equals x, you get the exact same thing, so its inverse is itself. In fact, it can be shown that this is the only function that has this property. Its inverse is itself. So, we have that the inverse of f inverse is equal to x. However, the reciprocal function is 1 over x, and if we graph these two, let's graph the reciprocal function in blue, and let's graph the inverse function in orange. So the inverse function, of course, is just the line y equals x, and the reciprocal function is the graph of 1 over x, which, as we are going to see in a bit, looks like that. Okay? Look, they're not the same. Not the same. So, do not ever write for the reciprocal function f to the negative 1 of x. Even though for numbers we will write this here, this is not correct for functions. Do not do this. Let me reiterate. You cannot write 1 over f of x equals f to the negative 1 of x. Do not even try and replace it. It's not going to work. Here's an example. It doesn't work, okay? So, not the same. And I really want to hammer this point home because it is super easy to make this mistake. You know, you're just going through your calculations, you're trying to write some stuff down, and you know, you're getting tired of writing 1 over f of x. You feel so tired, in fact, that you're thinking, oh wait, I know an easier way to write this. I can just write f negative 1 of x, right? That's the same thing. No, it isn't. It really isn't. And we're going to see even more examples of this when we reach the trigonometry unit. So, just as a general rule, do not make this mistake. Okay? It may seem that I'm overreacting on this part, but this is really, really easy to make. And it will cost you a lot. You'll be answering the completely wrong question if you replace 1 over f of x with f to the negative 1 of x. So, very quick and easy way to lose marks if you're looking for one. Alright, so now we're going to get to business. Remember, our goal was to figure out what properties of the graph of f of x we could carry over to the graph of 1 over x. So let's just go and start listing some things that we know. We'll consider a very simple example. We'll consider the example, let's do y equals x again. Okay? And the graph of y equals x is pretty simple. It's just a diagonal line. And the graph of the reciprocal function, you can graph it on Desmos, it looks like this. Okay? Now, I'm going to introduce some terminology here. So, a horizontal asymptote. So let me write definition here. You may notice that this orange is very vibrant compared to previous lectures. That's because I'm using another orange pen. I'll be using this one until it dies. It's been sitting in the cupboard for who knows how long. And the other one wasn't really working that well, so this is the one I'm using right now. So definition, a vertical asymptote is an infinite discontinuity at some point x equals a, such that the left and right sides of f at a go to infinity. Okay, this is the definition. If I ask you for the definition, you can either write this or you can write the more compact notation in limit notation. So all you have to write is limit as x approaches a is equal to infinity. Okay, or does not exist. Right. So I know I told you not to say that the limit here doesn't exist. However, notationally, we always write infinity because it helps us indicate whether the function is actually approaching something or is approaching nothing at all. So just for now, when you're trying to notate a vertical asymptote, this is what you're going to use. Okay. Another piece of notation that I want you to learn is the left and right side limit. So here, as you can see, let's just consider the point x equals 0. Okay. On the right side, this graph goes up and up and up and up to infinity. It never touches the y-axis. Okay, so this goes to positive infinity, and this one goes on the left side. It goes to negative infinity. All right. So the way we notate this is that the limit, as x approaches 0 from the positive side, that's what the plus means, of f. Sorry, I should put an f here. is equal to infinity, and the limit as x approaches 0 from the negative side of f of x is equal to negative infinity. Okay? And what we mean by this is that both the limits as x approaches 0 from the positive side, or a from the positive side, and as x approaches a from the negative side are plus or minus infinity. So let me just draw some examples of vertical asymptotes for you. So here we clearly have a vertical asymptote at x equals 0. Another example of a vertical asymptote is let's do one at x equals 1, right? And so here's a graph that has a vertical asymptote at 1. Usually we'll put a dotted line to indicate that there is a vertical asymptote. Of course, when you're doing it on the y-axis, when your vertical asymptote is at x equals 0, it becomes really hard to see because your dotted line is literally on the y-axis. So it's fine to like shift it a little bit left and right to show that, you know, there is a vertical asymptote there. And the dotted line, just for reference, just means that the graph never touches that line. Okay. So here we have a vertical asymptote at x equals 1. We'll always indicate it as VA for vertical asymptote. Okay. Of course, the only other types are just, you know, if this one went up and this one went down, or if both of these, instead of going both up, they both went down. Okay. But essentially, it's an infinite discontinuity from both sides. That's your intuition. However, when I ask for the definition, you should give this. This is the actual definition. Okay. If you say this paragraph here, that's not wrong either, right? This is precisely saying what a vertical asymptote is, but you can't just say it goes to infinity on both sides. Like, you actually have to say it is an infinite discontinuity at some point such that the left and right sides go to infinity, okay? And it is not enough to say that it's an infinite discontinuity. You have to be precise in saying that both sides go to infinity. So for example, this is not a vertical asymptote. This is not a vertical asymptote, okay? Because this side goes to infinity, but this side does not. All right? Okay. Now, just warning you, some people may have different interpretations of the definition. Some people will call this a vertical asymptote, like a one-sided vertical asymptote. For the purposes of what we're doing here, we are only going to call a vertical asymptote one where both sides are going to positive or negative infinity, okay? So this is a really important definition for you to know. I'm going to erase it now. It's a very important definition for you to know because when we're doing rational functions, you'll find that we come across these vertical asymptotes very, very often. Okay. All right, here's another one. We have the vertical asymptote's evil twin, the horizontal asymptote definition. A horizontal asymptote at y equals some number, let's call it b, occurs when limit as x approaches infinity of f of x equals b, or in this case means and or. Right? So both of these could be true, or only one of them could be true. It doesn't really matter. So this should be negative infinity equals b. Okay? Now, I'm going to assume that you don't really understand the limit notation fully yet, so let me just sketch it out for you. Eventually, by the end of the summer, though, you should be comfortable with reading this notation and understanding what it means. So remember what this means. This means as x becomes really, really, really big, okay? And b is just some point on the y-axis, so let's say this is b, okay? And a horizontal asymptote at b occurs when the function gets closer and closer and closer to b as x becomes really, really, really big, okay? And we will draw this dotted line to indicate that the function will never actually cross the line. It will just get infinitely closer to it and never touch it, okay? So we're going to do some practice after labeling the horizontal and vertical asymptotes. So here I've drawn a case where both the limit as x approaches negative infinity and the limit as x approaches infinity both approach b, therefore both of these are true. Okay, so we have a horizontal asymptote. We'll write HA at y equals b. Okay, and I've also drawn in this picture a vertical asymptote at x equals 0. Alright? Now, what questions can come out of this? Two really main types of questions will arrive out of this. Questions. So, I mean like questions that will be only involving things with this. We will have to deal with horizontal and vertical asymptotes all throughout the course. However, there are two main questions that I can ask that are just about horizontal and vertical asymptotes, okay? And they are the following. Okay, so firstly, I can give you a graph. So given a graph, what are the horizontal asymptotes and vertical asymptotes? Okay? And this one is pretty easy, honestly. The harder one is to draw a graph with some properties. Now, this was pretty tricky for you back in Unit 1, and what this is just an evolution of that problem. So now, instead of just saying, I want my function to decrease here, I want my function to equal this number here, and I want my function to, I don't know, do a quadratic thing on this interval, I can also say, I want a horizontal asymptote here, and a vertical asymptote here. So we're going to go through one of each type. Okay, actually, let's do two of each type. We can do this pretty quickly. Okay, so we're going to do the first question. So I'm going to draw two graphs, and I want you to label, just copy down the graphs roughly, and then I want you to label on these graphs what are the horizontal and vertical asymptotes, if there are any. Okay, so -1, -2. Okay, and that just means it's going way, 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 way up. Okay. On the other hand, here we will have okay. So I want you to label the horizontal and vertical asymptotes on both of these graphs. The first one here has a horizontal asymptote at y equals -1. So HA at y equals -1. Now this is fine. It doesn't matter that the function doesn't approach -1 on this side, because remember, we only needed one of the two to work. Okay. Here we have a clear vertical asymptote. Okay, and the reason why is because this side approaches infinity and this side approaches negative infinity. Because both sides approach n infinity, it is a vertical asymptote. Here, the situation becomes a little trickier. So of course, we have a horizontal asymptote here. I don't know what this number is. Let's call it like 2 or something, okay? So there is a horizontal asymptote at 2. And this is fine because both sides are approaching the value 2 as x becomes really, really, really big, and as x becomes really, really, really small. I mean negative, really, really, really negative. Okay? Now what happens here and here? I don't know, you can give these numbers, -3 and 3. I don't really care. The point is, at -3, both sides go to an infinity, right? This side goes to negative infinity, this side goes to positive infinity, therefore this is a vertical asymptote at x equals -3. However, this one is not a vertical asymptote for the reason that I just mentioned a few minutes ago, which is that both sides do not approach infinity. Here, this side approaches infinity, yes, but this side does not. It just approaches like some value in here, right? So like it takes on this value. So because of this, this makes 3, x equals 3, not a vertical asymptote. So this is no vertical asymptote. You usually don't have to notate this, but I'm just doing it for you right now, so you can see that there's actually no vertical asymptote here. So just to recap, vertical asymptote here, horizontal asymptote here, no vertical asymptote here. Okay, and get used to the notation HAVA. You're going to be doing it a lot in the coming few lectures. Okay. So now let's do example type 2, which is to draw a graph with certain properties. Okay. And here's where you have to be a little more creative with your work. So for example, I want you to draw a function that satisfies the following. Okay? And part A is going to look more or less similar to what we had in the previous couple of in unit 1. So let's do something that increases on negative infinity to 0 and decreases, actually let's union 2 to infinity, and decreases on 0 to 2. Okay? And I also want a horizontal asymptote at y equals 2, a vertical asymptote at x equals, let's do 1, and then, let's see, what can we do? I think that's about all I want to do. And then for part B, a little harder one, we're going to increase on the interval negative infinity to negative 3, union 0 to 3, union 5 to infinity, decreasing on the interval negative 3 to 0, 3 to 5, and I want to, let's say, f of 0 equals 1, but there is a vertical asymptote at x equals 3 and x equals negative 3, a horizontal asymptote at y equals 2. Right? So we're going to take these examples and you will get to see how I tackle each of them. So this one, okay, so remember how when we were discussing, I said the most important thing for you to do was to tackle the most stringent conditions first. The new most stringent condition is now not just a labeling of a point, but it's actually these asymptotes. These asymptotes really dictate what you can and cannot do, especially the vertical asymptotes. So let's go and label those first. So this is x equals 1, put a dotted line here, okay, and y equals 2. So let's put another one here. So here's our horizontal asymptote, here's our vertical asymptote at x equals 1. Maybe I'll make that clearer. And y equals 2. Now we just want something that increases all the way up until 0. So let's see. I'm going to do this. I'm going to write, like from here to here, I want it to go up. I'm just going to draw the general direction. And then I also want it to go up from 2. Let's say this is 2. Okay. So I want it to go up in this general area. But then I want it to go down in this general area. So I want to go down. Right? So now you just have to follow what is dictated by everything. So let's see. The horizontal asymptotes, what you can do is you can, okay, well just think about it. Let's say I wanted to do my horizontal asymptote only on this side. Okay, actually, let's do it on both sides. Let's do it on both sides just to show you that it is possible. Okay, so what we're going to do, I'm going to do it in orange because it shows up really well against the blue. And we're going to try and draw from here. Okay, so yeah, look, if I do this, then the limit as x approaches negative infinity is equal to 2. Aha, so we got our horizontal asymptote. And I'm going to keep drawing. Oh wait, you got to pay attention to this, right? Here it says we need to increase, right? But look what I'm doing, I'm immediately decreasing. So the question is, can I really increase here? I mean, yeah, it technically works, but I mean, you're better off just going on the other side of the dotted line. It's like this, okay? It's just a logic puzzle, okay? If you can't increase going from the bottom of the dotted line, you have to use the top of the dotted line, okay? So you're increasing all the way up until x equals 0. Aha, now I have to start decreasing, okay? So I'll start decreasing. Oh, but then something else happened, right? We ended up getting a vertical asymptote. Right, so, okay, this thing has to decrease. Okay, so what does that mean? That means it has to be going down, okay? And there's a vertical asymptote, which means it has to reach infinity. So can this line go all the way up until positive infinity? Well, that doesn't make sense, because if it went up to positive infinity, that means it would have to increase somewhere. So that means it has to go to negative infinity. So I'm going to make my line just dip way, 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 way down. Notice that it doesn't matter if it crosses the horizontal asymptote here, as long as the limit in the limit, as x goes really, really, really big, it eventually never touches the horizontal asymptote anymore. Okay. So this is a perfectly fine way to do it. Now here, I want it to continue to decrease, and I still need a vertical asymptote. So I'm thinking maybe I'll go from here, right? I need to go from n infinity, so let's just choose negative infinity. So we'll go from here, but look, if I start going up here, I'll be increasing. Here I was supposed to decrease. So this is going to be a problem. We can't choose negative infinity. There's no way it's going to work. We'll choose positive infinity then, and then, aha. Okay, so here's the problem now. Here's the problem. So we need to make sure that at 2, we start increasing instead of decreasing. So what we'll do is that we'll dip below and then start increasing again. So that's one way to get around it. Okay, so right about at 2, we'll start increasing again, and then we'll go and meet our horizontal asymptote. Okay? Or we didn't even have to do that. We could just do something like that. It didn't really matter. Okay? But if you wanted a horizontal asymptote here, it's definitely possible. You just have to make sure that you're increasing to the horizontal asymptote. Remember, you could not be going down on this side, because or else you would not be decreasing on this interval. Right? So this is another more strategic way of doing these types of examples. And as you can see, you got to be quite careful. It's very easy to miss a lot of detail here. Next example, and this one you can try on your own. Okay, this is tough. There's just a lot to take in here. So I'm going to make a big graph, label my points -3, 0, 3, 5, and I have a horizontal asymptote at y equals 2, vertical asymptotes at 3 and -3. Okay, so I'll draw my dotted lines at 3, -3, and 2. Okay, dotted lines everywhere. Now, I'm going to also label my increasing and decreasing intervals, but before I do that, remember the most stringent condition that you can impose on a function is literally saying what a point is. This f of 0 equals 1 corresponds to the point 0, 1. You plug in 0, you get in 1. So the x value is 0, the y value is 1. X value is 0, y value is 1. So that's this point here. So we know our function must pass through that point. Let's label where we need to increase. So from here to here, we need to go up. Then we need to go up on 0 to 3. And we need to go up on 5 to infinity. So 5 to infinity. Okay? And then everywhere else we're decreasing. So I'll do that in red. I just do this to give myself the general direction. And eventually, as you get very good at this, you can start leaving out some of these little things. But for now, because this is our first time and this is a very complicated example, we have to go through all the steps. So what I want to do now is, let's see, horizontal asymptote at y equals 2. So I don't know, let's just go above, right, and see what happens. Aha, going above will work because I want to go up, right? So I can just keep going up. And I see that I'm approaching a vertical asymptote, so why not just go ahead with it and keep going up? Okay? Fine. But now, what do I do here? Can I start from negative infinity? No, I can't, because if I start going from negative infinity on this side, remember, this is a vertical asymptote, so I need to go either from positive infinity or negative infinity. If I start going down from negative infinity, there's no way for me to go. Like, you can't go lower than negative infinity. It's not possible. So that means that we can't start from here. We must start from here. Okay? And we'll go down, we'll go down. Remember, it doesn't really matter if we cross the horizontal axis at this point. Sorry, the horizontal asymptote at this point. But remember, it does have to cross this point. So let's just cross that point here. Okay? And then, aha, now we have to start going up again. So let's start going up again. I don't know, we'll maybe do that. Aha, we're meeting another vertical asymptote, so let's just go up, right? We can go up. All right, now what? Now what? Okay, so we have to go down again, right? So what if I try going from here? Oh, but then we run into the same problem we did here. if we need to go down, we can't start from negative infinity. We have to start from infinity. You can only drop from a higher place. So you start from up here, and you start dropping, okay? And you're dropping until 5. What happens at 5? You need to start increasing, okay? Now, because I already took care of the horizontal asymptote here, I don't need to, but I will just for now, okay? Notice I had to drop below this line, because if I did not, that means I would have to do this, right? And here, I'm decreasing. I was supposed to be increasing, right? So I need to be below the horizontal asymptote. So go below it, and then as soon as I touch 5, I'll start going up again. So let's just do that. Okay, just like that. So here, this way we have our horizontal asymptote at y equals 2, and our vertical asymptotes, check, good. So vertical asymptotes here, and vertical asymptote here. And let's see, f of 0 is equal to 1. Let's just make sure that we are increasing and decreasing in all the right places. So here we need to be going up, and then down, and then up, and then down, and then up again. So this is correct. Okay? Good, so this one was a trickier example, but hopefully you can see that this strategy that I'm bringing basically makes sure that you can't really mess anything up unless you're not paying attention to what is on the board. Alright, so now we are proceeding to the main part of the lecture, which is where I'm going to show you how, given a function, you may try and attempt to draw its reciprocal function. Okay? And we will notice once again that it is not the same as the inverse function, because we will see that when we draw the reciprocal function, it will pretty much never look like the inverse function. It will never be a reflection in the line y equals x. Okay? So let's start just by naming and listing some things that we might expect from a reciprocal function just from our intuition about numbers. So for example, let's see. Let's take a graph, right? And I don't know, maybe it does something like that. And we want to figure out what its reciprocal function is, okay? The first thing I'm gonna think about is this point right here, okay? And why do I want to think about this point? Because, no, I don't want to think about the point. Okay, so now we're going to proceed to the main part of the lecture, where I'm going to describe how, given a graph, you might attempt to reconstruct a reciprocal function. We will see in this part that the reciprocal function pretty much is never going to look like the inverse of f. So what we're going to do is we're going to start by picking out some properties that we would expect would carry over from the original function to the reciprocal function, and figure out how to make a sketch from there using what we know about creating sketches of functions just by brief descriptions of them. Okay? So firstly, what does the reciprocal function really do? Think about what the original function does. So f of x takes in some number x and outputs a value y. The reciprocal function 1 over f of x, right? What it will do is that it will take in the same value x, and what will it output? It will not output y, but it will actually output 1 over y. Okay? So the y coordinates of the reciprocal function are always going to be the reciprocals of the original y coordinates of the function. That's pretty much exactly stating what a reciprocal function does. It just takes your function values and does 1 over that. So there's not really much that's interesting there, except for a couple of things. When we do this reciprocal operation, something interesting happens. Right? So let me put in the corner here, x gets sent to y in f, but then the 1 over f function sends x to 1 over y. Okay? What happens, question, what if y is 0? Then we have a problem, right? And our problem is, of course, that this is going to be undefined, right? we get an undefined point. Okay? In fact, it can be shown that this point, x, is a vertical asymptote. Okay? We get an undefined point. So let's see. What if y equals 0 when we do f of a? Then x equals a is a vertical asymptote. Okay? So just graphically what that means is that here's f of x, and here's the graph of 1 over f of x. Okay? I'm going to just draw like a segment of the graph. Let's say your graph does this, and whenever it hits 0, right, let's see this point is like 3 or something. That means we're just going to get a vertical asymptote at 3. Now I don't know exactly right now how this vertical asymptote is going to look like. All I know is that it's going to be there. Okay? Maybe it's going to look like that, maybe both are going to the bottom, I don't know. But we're going to figure more about that later. Okay? So x equals a is a vertical asymptote. Alright, here's another question. What if at the point xy we have a local max? Okay? Then what happens? Okay, so what does a local max mean? It means that in a neighborhood around the point, so again we have our function here, so let's say we have a point here. Remember, the definition of a local maximum, this is the point a, f of a, and this is the graph of f. A local max means that f of a is greater than f of b, where b is close to a. Okay? So what happens at the point, let's call it a, f of a? We have a local maximum. When we take the reciprocal, what's going to happen? Well, remember, if you have a really big denominator, your number is actually smaller, right? So let's say a is greater than b. That means that if we do 1 over a, it will be actually less than, sorry, I'll switch it around. If we do 1 over a, it is actually less than 1 over b, because this is a bigger number, so its fraction is smaller, right? So perhaps you could see, just intuitively, that that means that here, it would have to, when you do the reciprocal function, it would have to turn into a minimum. So in the reciprocal function, the point, now it's going to be a 1 over f of a, because remember, if we send x to y, it gets sent to 1 over y. In the reciprocal function, a 1 over f of a is a local minimum. Okay? Similarly, a local minimum in f will become a local max in 1 over f of x. Okay? So what I'm going to do is, because that took up a lot of space on the board, you can write that out fully, but all I'm going to do is write here, I'm just going to go and write that min becomes max and max becomes min. That's the short way of remembering it. Min becomes max, max becomes min. Okay? Next question. Okay. If f of x is positive on some interval ab, then what happens? Well, remember, when you take the reciprocal of a number, that doesn't change the sign. So 1 over f is still positive on the interval ab. Similarly, if f of x is negative on some interval ab, 1 over f of x is also negative. And this just comes from the fact that if you do 1 over a number, that doesn't change the sign of the number. All right? So let's abbreviate this as well. We will say that the sign, the signs of the function, the signs, which means plus or minus, of f of 1 over f of x are the same as f of x. Okay? Next question. Yeah, there's a lot of these. And it sort of ties into this one, right? So if you have a function that increases, right? When you take the reciprocal of all those numbers, these numbers are very big, so when you take their reciprocal, they're going to become very small. So actually an interval of increase is going to become an interval of decrease. Okay? So question, what happens on intervals of increase and decrease? Well, it's the same idea here. So increasing intervals become decreasing intervals. You should probably write out the full thing in your notes. I'm just going to write it in shorthand here. So increasing becomes decreasing, and decreasing intervals become increasing intervals. Okay? All right. Yet another property that we will get is this. If f of x is a polynomial, we have a horizontal asymptote at x equals 0, and both sides, so x going to infinity of 1 over f, we're considering 1 over f, negative infinity of 1 over f is equal to 0. So that means both of them eventually will be going to 0. So for example, it might look like that, because they're both going closer and closer to 0, never touching. All right? So those are all the facts that we are going to be really using. There are a couple of other ones that you could mention, but they're really not worth it because they aren't going to really help you in the end. Okay? All right. So I think what we're going to do now is just give you the procedure for figuring out what the reciprocal of a function is. Okay? Here's the issue, though. Here's the issue. Because sometimes, instead of being given the original function, you might just be given an equation for the original function. You may not be given a graph, you may be given the actual equation, in which case you have to graph f first, and then graph 1 over f of x. Okay? And that is usually a very tricky process. Okay. All right. So when we're doing this, so when we're doing this, here's how we are going to do the reciprocal function. So graphing reciprocal function. And we need to divide this into 2 steps. Okay, here's the procedure. Let's see. Okay, so plot f of x. Okay, we have a lot of tools for plotting our functions, but we're going to have to take some note of some things. Okay, so when we're doing this plot, what we want to do is figure out where f of x is greater than 0 or less than 0. The next thing that we want to do is we want to figure out if there are any zeros, so identify roots. Okay. Then you need to see intervals of increase or decrease. So intervals of increase or decrease. So you need to make note of all of these things in the original function. And then you need to label or take note of local max and min. Actually, it doesn't matter whether they're local or absolute. Just make sure you take note of all the max and min. Okay. This is just a very comprehensive checklist. As you get better at this, you may find that you may not need all of this, and we're actually going to go through a more general procedure in the coming lectures that will help us graph more than just the reciprocal functions. This is just sort of like your first step towards that direction. Okay. Your second goal is now to plot 1 over f of x. Okay, and here's how you do it using all of this information. Okay. So your first step, let me do it in a different color actually. Let's do it in blue. So graphing 1 over f of x. Okay. So your first step is to try and find the y-intercept. Okay. Remember, what does a y-intercept mean? It means that on a graph, it means that x is equal to 0, right? So let's say your y-intercept's here. That's the point that happens when you plug in x equals 0. So really what I'm saying is set x equals 0 and just plug it into 1 over f of x. Okay? So 1 over f of x will be your y-intercept. The next thing that you want to do, so that will give you like 1 point. Okay, that's fine. Good. Now from the tricks that we learned earlier, you are going to label immediately the horizontal asymptotes and vertical asymptotes. This one only if you know that they are there. So the preliminary examples that we're going to be working with will all have horizontal asymptotes. So we'll just stay with that. Okay. Yes. So you need to take note of your horizontal asymptotes and vertical asymptotes using the steps outlined previously, or using the tricks outlined previously. Okay? All right. Let's see. Take note. So using this, you need to sort of switch around the intervals of increasing and decrease. Okay. Next up, you need to figure out the domain and range. Okay, this one is going to be a little tricky. Okay, I'm going to say that you're going to most of the time ignore the range. The really important thing though is to figure out the domain. So the domain is the same as the domain of f of x, except, and this is the big exception, and that comes from here, right? So except when f of x equals 0. When f of x is 0, 1 over f of x is undefined. Okay? Very important that you take note of this. But if you follow this procedure, you would have already taken care of that. So this one's sort of like it's not a super big deal. Okay? Finally, you are going to note points that are maxima or minima. Okay. Now, this thing here, this stuff about maxima and minima, we are not going to focus too much on that right now. So this one's going to be like less focus. Okay. So what you have up here and what you have up here are the most important things to take note of. Okay. There's only one last thing that you need to be super sure that you take note of, and maybe I will write it. Let's see. I'll write it up in the corner there. So 1 over f of x is greater than 0 whenever f of x is greater than 0 and is also less than 0 whenever, and this is just a point that we made earlier, the sign of the function does not change, right? And so you'll use, let's just draw it in, you'll use this fact to help you with that one, right? So those two are linked. The roots, of course, you will use to identify the vertical asymptotes, which in turn will allow you to identify the domain. Okay, right? Identify roots is the same thing as f of x is equal to 0. Okay, and then to further complicate this diagram, the intervals of increase and decrease will inform you of the intervals of increase and decrease in your reciprocal function. Okay? So everything I highlighted in red, orange, and red are the most important points to take out of this. Okay? This one is also important. And yeah, that's about it. Okay, so let's go through some examples to sort of clarify this process. We're going to go through, I'm going to try to do, let's do 2, 3. I have 3 examples. I think I'm just going to do 2. All right. Yeah, we're running a bit low on time. So, I think I'm going to get rid of this now. I think it's been made abundantly clear that this is very, very different from the inverse function. Just one last warning, please remember this because it's super common, and if you're not paying attention and you're using your notation badly, this will mess you up. Okay, so let's go ahead and do this process for the function f of x is equal to 1 over, actually we're going to let f of x equal x minus 1, and then we want to graph the reciprocal. Okay? So what is the reciprocal? It's 1 over f of x, which is the same thing here as 1 over x minus 1. Look, I literally just took this and put it in the denominator. Okay, pretty easy. So what is our procedure again? We need to graph x minus 1 and take note of a couple of things about it. Okay? So this one's pretty simple. Right? It's just a line. You've been graphing lines for a very long time now. You're probably tired of it. But back to the basics. So we know that it's increasing everywhere. Increasing everywhere. I'm also going to take note of its 0. So root at x equals 1. Let's see, what else do we have? We also have... I think this is, yeah, because there's no local max or min. And the domain is everything, right? So this is pretty much everything that we need from the original graph. Let's see and try, let's try and see if we can graph the reciprocal function just using this. And if we're lucky, we won't run into any problems. Okay. So now check your notes and figure out what you want to do first. I want you to try and come up with the reciprocal graph on your own first and then watch how I take care of it. Okay? So first order of business is to note that this is a polynomial. Okay? Remember with a polynomial, we said earlier that limit as x approaches infinity and limit as x approaches negative infinity of 1 over f, they're both equal to 0. Okay? So that means that eventually our function is going to have a horizontal asymptote at x equals 0, at y equals 0, sorry. Y equals 0. Alright, so now that that's out of the way, we can see that here the function's negative. So that means everywhere behind this, it also has to be negative. So let's draw 1 here, right? But remember, at our roots, we need to have vertical asymptote. So let's put another asymptote here. So vertical asymptote at x equals 1. Alright? And remember, we just said that here you need to be negative, and on the other side you need to be positive. And that's just because on this side, before 1, your function is negative, and after 1, your function is positive. So the sign is the same when you do the reciprocal function. Okay? Now, we notice here that it's increasing everywhere, which means that over here, we have to be decreasing everywhere. And now, we have pretty much everything we need to graph this, believe it or not. Okay? It's, again, just a logic puzzle. Okay? Let's just do one thing quickly. Let's figure out what the y-axis is. Sorry, the y-intercept is. And if you notice quickly, if you put a 0 in here, you'll get 1 over negative 1, and that's negative 1. So that means the y-intercept is just negative 1. Okay? So, facts. We need to go through this point. We're going to be below the x-axis the whole time, and we're also going to be decreasing. And there's a vertical asymptote here. So that forces you, that literally forces you to make your function look like this. Okay? If you did not draw something like this, you definitely got it wrong. Okay? The key point is that it's not going to touch the horizontal asymptote. It's going to go through the point, and it's going to go straight down. Okay? No funky stuff. Same thing here. Okay? It's a logic game. Of course, this is a vertical asymptote, and we can't come from the negative side because we know that our function has to be positive after 1. So we'll start up here. We have to be decreasing, but that's fine because we're just going to meet our horizontal asymptote just like that. Okay? And that's it. That's the graph. 1 over f of x. Okay? So that is how you graph a simple linear reciprocal function. All right, on to our next example. We are going to try one that is a little trickier and will involve a little bit more work on our part. All right. Let's try the quadratic. Let's see, which one do I want to do now? Yes. So let's do the quadratic f of x is equal to x squared minus 6x. Okay? And of course we want to graph our reciprocal function 1 over f of x, which is just 1 over x squared minus 6x. I hope you immediately see that this is factorable, so you should factor it. Okay? And because we get in a factored form, the graph is actually quite simple to do. It just looks like this. So 0 and 6 are our roots, and our graph opens upward because there's a positive sign in front of the x squared, so we know our function is going to look like that. We should take note of the minimum here, so you can just figure out the minimum because it's the value like between 0 and 6, so I just plug in a 3 in here, and use whatever method you have for finding the vertex of a parabola. I know you learn this and do this a lot in grades 10 and 11. So I'm not going to try and impose a new method on you. All I'm just going to say is that 3, if you plug 3 in here, you get the answer really quickly. All right, so let's see. 3 times negative 3 is negative 9. So this is actually negative 9. Okay? It doesn't look like negative 9, but you know that's what it is. That's what it turned out to be. All right, let's take note of what is going on here. So it is negative in this interval. So here is negative, and everywhere else is positive. It's positive, and here it is negative. Then we're going to take into account decreasing and increasing. So from here all the way up until this point, it is, and remember this point is at x equals 3. So this point it is decreasing, and after that it is increasing. Okay? I have the advantage of being able to use colors. You will have the disadvantage of only being able to use pencil on your tests and quizzes and homework. So be sure that you get comfortable doing this and find your own way that works for you. Okay? Sometimes I can keep track of everything in my head, but when I was doing this in school, I typically wouldn't write anything. I would just try and do it my own way. But if you're having trouble keeping up with all the details, it's good to write stuff like this. I think this will really help. Okay, so armed with this knowledge, I think we can begin to start trying to graph the reciprocal function. Okay, I'm going to graph it on a different graph just to speed up the process. All right, right, so we have roots, right? We have roots at 0 and 6, okay? So that means we're gonna have vertical asymptotes there. And aha, our graph is also a parabola, so that means, of course, we're gonna have a horizontal asymptote at x equals 0. So we're gonna have a vertical asymptote here. Sorry, this is a y equals, I keep on saying x, I don't know why. And then another vertical asymptote here, x equals 6. All right. So we'll just start trying to draw it here, okay? First, y-axis, right? Does it have a y-intercept? If you think about it for a little bit, you'll realize that it's impossible because when I put a 0 in here, I get 1 over 0, and of course that's not a number. But you should have seen that coming because we have a vertical asymptote here. By definition, a vertical asymptote is undefined. Okay? Your function never takes on that value. It's a vertical asymptote. Okay, now what? Let's try and tackle the plus minus plus. So that means that from here to here, I'm just going to draw it on the bottom. So here we're going to be plus, and then from 6 onward, we're also going to be positive. But then from 0 to 6, we have to be negative. Okay? So if we're negative here and we're positive there, that kind of forces our hand a little bit, doesn't it? Okay, but we'll see. We'll see about that. Okay, well, consider increasing and decreasing, right? So, of course, they have to switch. So that means at 3, let's call that 3. Okay, we have to start decreasing instead of increasing. And on the other side, we have to, of course, increase. All right, that is about all the detail that we are able to get immediately for our reciprocal function. So let's try and graphing it and see what happens. Okay. So we know it's positive, so that means it's going to be up here somewhere, and we know it's increasing. Okay. Well, we know there's a vertical asymptote. A horizontal asymptote here, a vertical asymptote here. Of course, it can't be the negative one, so it has to be the positive one. And then we'll just connect the line and see that it works because we're increasing, right? We're still increasing. Next, what happens? Right here. We're negative, so we have to be in this like box that I've drawn here. Now what you do is, of course, you have to have a vertical asymptote here and a vertical asymptote here, because of course it can't be the positive ones. I told you you had to be in the box, so stay in the box, right? Now we are increasing up until this point, okay, and then decreasing right after. All right, so I satisfied that. The only thing is that this here, right, this is dictated by what happened here. Remember, this is a local min, which means that corresponds to a local max, right? What is the local max? It's going to be the reciprocal of this. And the reciprocal of -9 is 1 over -9. So this point here is actually 1 over -9. If it so happened, this is impossible, but if it so happened that it was a positive number, then yes, I would have to keep going up there. Okay, but that's impossible because we said this entire section of the graph had to be below the x-axis, right? So finishing off, again, it's still a logic puzzle. Here we have to be above the x-axis, so we have to be in this region up here, and we have to be decreasing, so that means we have to be going from here, and then horizontal asymptote to 0. And this is our sketch of the graph. Okay, you can actually graph this on Desmos and see that it's actually quite accurate. Okay. All right, I think I ran through those examples a little faster than I intended to, so let's go ahead, backtrack a little to do another one. Okay, I think I'm gonna do, yeah, this one's a little bit more difficult, but it's more or less the same as this in terms of difficulty. It's just I think you would benefit from seeing another example. Keeping track of everything is of course a little bit tricky, and if this is your first time doing it, it's very tricky. But hopefully you're starting to get into a rhythm of it now. It's really just becomes a dull pattern after you do it a couple of times. So I try not to make things too repetitive, but you know, at the end of the day, the important thing is that you're able to solve a question. You know, you can't solve questions without some practice. So that's what all of this is for. F of x is equal to x plus 1 squared. X plus 1 squared minus 4. You know what's really convenient about this? What's really convenient is that it has been given to us as a transformation of x squared. So we can just immediately draw this as a translation, 1 left and 4 down. So we'll go, the vertex is going to be here at -1, -4, and it's just going to open up like that. Okay, let's figure out the roots, right? So there are roots here and here. I don't know what those roots are, but I will go ahead and label this point a local minimum just for future reference. Okay. I will also immediately note, actually let's figure out the roots first, and then we'll talk about intervals of increase, decrease, positive, negative, and so on. Okay, so remember, when we're doing this, we need to solve for 0, because that is what finding a root means. We need to solve for 0. Throw the 4 onto the other side, you get x plus 1 squared equals 4. Be very careful here and apply square root to both sides. Okay? When you do this, you need to take the positive and negative square root. So you get x plus 1 is equal to positive -2, plus or minus 2. So let's split this up into 2 cases. X plus 1 is equal to -2, x plus 1 is equal to 2, and x plus 1 is equal to -2. In this case, we get x is equal to 1, and in this case, we get x is equal to -3. Okay? Just quickly checking, if you plug in -3 in here, you get 4 minus 4, which is 0. If you plug a 1 into here, you get, again, 4 minus 4, which is 0. Okay? So this point here is -3, and this point here is 1. Okay? Watch how I was very careful with the square rooting. Okay? You don't want to be making a mistake with this, right? For example, you can't take a square root first and then move the 4 over to the other side. It doesn't work like that. Okay? So here's a very common mistake that people might try, which is this. X plus 1 squared minus 4 equals 0. You might think, aha, well I can just take a square root, right? Because I want to get rid of the square. I might do that. And then that'll give me, of course, x plus 1 minus 2. Aha, and then I'm going to get x minus 1 equals 0, x equals 1. This is horrible math, okay? This is wrong, and this is wrong, and this is wrong. The whole thing is wrong, okay? Be very, very careful when you take your square root, okay? You can only use the square root on something that is squared. If it has a minus something inside it, not going to work. You can't cancel out anything. Okay? So again, I was super careful here. I square rooted only the thing that was completely squared. All right. Now we can start talking about intervals of increase, decrease, positive, and negative. So of course, from here to here, I'll try to draw my line straight this time. We're negative. And we are decreasing from here onward, so we'll make a note there. So we're going to decrease. And then everywhere else is going to be positive. And everywhere else is going to be increasing. Okay? Just your basic stuff. Now, let's try and tackle this reciprocal graph. F of x is equal to 1 over, what is it, x plus 1 squared minus 4. Okay. Again, this is a polynomial. You can expand this thing out and you will find that it is a polynomial. Therefore, it will have a horizontal asymptote at y equals 0. Aha, I said it right this time. Let's see. What can we do first? Right, we should try the y-intercept first. Oh, we should do the vertical asymptotes first. You see, I'm very free-form when I do this. I don't really have a plan of what thing to tackle first. I'm trying to keep it consistent for your sake, because it's your first time learning. But as you get good at this, the process sort of becomes random, and you do what you like. And soon enough, you'll get enough experience that you don't even have to do this method anymore. You'll be just graphing using what we call an interval chart, which is something that you've seen before, but we're going to apply it to rational functions, which is really exciting. It's like the next level with these polynomial inequalities. Okay. Right, I think I wanted to find the y-intercept first, right? So if I plug in 0 here, what do I get? 1 minus 4 is minus 3, so that means that a y-intercept is negative 1 over 3. Next, I want to graph the intervals of increase or decrease, right? So here we're positive, right? So it means we have to be staying in this box right here. And so we're sort of forced to do this, right? We can't really exit the box, and we have a horizontal asymptote here, a vertical asymptote here. You're kind of strapped. You can't really do anything. But here, you know you have to go through this point, and you know that you're negative. So let's try and do this. Okay. Does that work? Think about it. Really think about it. Does that work? I hope you caught me because I intentionally made a mistake here so you would try and notice it, which is that here we were supposed to be decreasing, but instead what we're doing here is increasing. Okay, so that means we have to change our diagram a little bit. And the more you look at it, the more you realize, aha, here's the mistake. Right, it's here. It's this. Right. So what was going on here is that this thing was positive, and then it was negative. So that means, what? Okay, now I'm confused. Oh. Right. So. Okay, so let's just check to see if this is right. What we're going to do, actually I should note this down first. So let's check to see if this is correct. The way we're going to do it, of course, is we're going to make sure that these things switch. So that means after 1, here's 1. After 1, we're going to be decreasing. And before 1, we're going to be increasing. Notice that we were supposed to stay in the negative zone, so that means we had to stay in here, and we pretty much we were only forced to do this. Okay. One small refinement I can make to my drawing is making it more clear. Sorry, that the maximum is at this point. X is equal to -1. So there. I mean, it's not perfect, but you know what it'll do. Okay, and we can actually figure out what that point is. Let's take care of it now. So remember, it was a local min. That means it becomes a local max. Okay, so this was the point, -1, -4, which means in the reciprocal function, it becomes -1, 1 over -4. So this is actually -1 over 4. Okay? Next. And yeah, everything's fine because we were increasing here and then decreasing right after. Here, we were supposed to be positive. We have to stay up here, and once again, we have literally no choice for what we can do. It has to look like that. You can check that this satisfies all the requirements, and we are done. Okay. So hopefully those 3 examples were more than enough to show you how to graph these basic polynomials. The only polynomials that I would say you would have to graph this way are ones that look like what we've just done here. Nothing really too crazy for the most part. Maybe I'll throw in a cubic just to test if you can factor it out and stuff like that. But you know what? It's at the end of the day, it's really not that difficult.